Today I'm going to present our work on using Geotagged social media to model human mobility. This is a joint work with researchers from Hefei University of Technology and the US Army Research Lab. So the task of mobility modeling aims at understanding the underlying regularity of human movements, such as where do people stay in their daily life and how do they move from regions to regions. It's a quite important task because it can benefit various applications like urban planning, traffic scheduling, and location prediction. So mobility modeling has been studied quite extensively in the past few decades, but most of the previous studies used the GPS trace data for this task. But in recent years, the popularity of Geo-Tagged social media brings new opportunities to this task. For Geo-Tagged social media, it has two unique advantages compared to the conventional GPS trace data. First of all, in addition to the spatial and the temporal information, each Geo-Tagged social media record also has the text information. So we can understand not only where the user is, but also what the user is doing. And second, the Geo-Tagged social media has a much larger size and much better coverage. While the GPS trace data are usually collected by involving a number of volunteers, the Geo-Tagged social media providers allows the users to make posts from anywhere and at any time. So millions of Geo-Tagged tweets and Facebook posts are created every day. So we claim that the Geo-Tagged social media is a very valuable data source for understanding humans' mobility. So our goal is to use large-scale geosocial media to unveil the human movement regularity. Specifically, we answer two questions. First, we want to understand what are the intrinsic states underlying people's movements. Here, a state should provide unified 3W view regarding the user's activity. That is, where is the user, what is he doing, and when does this activity occur? And the second question we want to answer is, how do people move sequentially between those latent states? For example, what will a user do after working at the office and after having dinner at the restaurants? Using geosocial media for mobility modeling is not an easy task. There are two challenges we are facing. First one is the dilemma for applying the mobility model. If we apply the mobility model at the individual level and try to learn a model for every single user, then we suffer from data sparsity because a typical geosocial media user only has a limited geosocial media records. So learning a model for every individual is not reliable. And on the other hand, if we try to learn one model for all the users, then we suffer from data inconsistency because different users can have totally different moving behaviors. If we learn one model for all the users, then the different moving patterns are mixed up. And this is the first challenge we face. The second challenge is the geosocial media mostly have very short text. For example, in tweets, the length of the text is limited to 140 characters. So the short text makes it very hard to model the semantics of the human activities. To address these dilemmas and the text sparsity, we proposed a model called the GMove model, which is based on Hidden Markov Model. There are two key modules in GMove. The first one is HM ensemble learner, which performs group-level mobility modeling to try to learn an ensemble of HMMs. And the second one is a text augmenter, which tries to reduce text sparsity using spatiotemporal signals. In the following, we will elaborate those two modules. So let's first look at the first module, the HM ensemble learner. First of all, let's look at how we can apply Hidden Markov model for mobility modeling. The Hidden Markov model is a very popular statistical model for sequential data. In order to apply Hidden Markov model for mobility modeling, we consider the location history of a user, which is a sequence of locations. Then Hidden Markov model assumes there are multiple latent states, such as working at the office or having dinner in restaurants, that governs the user's movements. The sequence of the latents follows the Markov process. In addition, every latent state generates an observation. In our case, the observation is multidimensional that contains a location, a time, and a text message. Given a collection of users' trajectories, the Hidden Markov model tries to infer the latent states and also the transition probabilities between latent states. But as we mentioned earlier, directly applying hidden Markov model on the geosocial media is quite tricky. Because if we try to use HMM at the individual level, then we suffer from data sparsity because each user has a very limited number of records. On the other hand, if we try to apply HMM at the global level, then we suffer from data inconsistency because different users have quite different moving patterns. To address this dilemma, we propose a strategy called group-level modeling. The key idea is that there are multiple user groups that have similar moving behaviors. For example, a group could be a group of Stanford students or San Francisco tourists. We try to find the latent groups and train an HM for each group. In this way, we can reduce data sparsity by aggregating the movements of multiple users in the same group. At the same time, we are not compromising data consistency because the users in the same group share quite significant movement regularity. Now the question is, how can we find such quality user groups? We claim that user grouping and mobility modeling are not independent tasks. Instead, they can mutually enhance each other. Suppose we have better user grouping, then we have more consistent movement data within each group, which can improve the quality of the HMMs. On the other hand, better HMMs can better reveal the movement regularity, which helps us infer the group a user belongs to. Based on this observation, we propose an iterative process that alternates between user grouping and HMM training. In the HMM training phase, we assume the group memberships of the users are already known and fixed. Then we learn one HMM for each group. And in the user grouping phase, we assume the HMMs are already learned. Then for every user, we update the membership vector by computing the posterior probability that the user belongs to the group. In our paper, we have proved that such an iterative process will finally converge to generate quality user groups and the HMM ensemble. Okay, now let's look at the second module, which is the text augmenter. As we mentioned earlier, the text augmenter is necessary because the raw text message is very short. So we attempt to use the spatiotemporal distributions of different words to unveil their semantic correlations. Such correlations can be used as auxiliary knowledge to help us better model the semantics of users' movements. As a concrete example, let's consider two users that are watching the same Lakers game at the Staples Center. Those two users may post tweets using two different keywords. Maybe one user used the keyword like Lakers and the other used Staples Center. Those two keywords do not co-occur in the same tweet, but they are correlated because they are posted at the same location and around the same time. So we try to find correlations of different keywords based on their spatiotemporal distribution. For this purpose, we consider a three-dimensional cube, where the three dimensions are the time, latitude, and longitude. We discretize the whole cube into equal-sized cells. Then for any keyword, we can compute its distribution over the three-dimensional cube to obtain a vector. Then given any two keywords, we compute the cosine similarity between their vectors as their semantic correlations. After computing the correlations between different keywords, we perform a very simple sampling process to augment the raw text message. Specifically, for any given text message, we first pick a word randomly based on the TF-IDF weight. Then we choose a new word based on the strength of the correlation. And we add the new word into the augmented message. We repeat this process until the length of the augmented message is good enough. Now let's look at some experimental results. In our experiments, we use about 0.6 million Geotag tweets published in LA, and also 0.7 million Geotag tweets published in New York. In the first set of experiments, we perform a case study to look at the effectiveness of the text augmenter. In this table, the middle column shows the raw tweet messages. As you can see, all of those messages are pretty short. For example, the first message is talking about a basketball game of the Lakers, but it mentions only a few keywords like Kobe, Lakers, and fans. But after the text augmentation, we can find many other related keywords, such as game, Jeremy, injury, staples. Those keywords do not occur in the original raw tweet message, but they are very correlated. So after the augmentation, we are able to connect different tweets together that are talking about the same game to better understand the semantics of the user's activity. And we have similar observations for the other tweet messages. In the second side of experiments, we show 2 example group-level mobility models. What we did here is we set the number of groups to 10, and then we run GMove on the LA dataset. Out of the 10 result group-level mobility models, we choose 2 representative ones. And we find that the first one corresponds to the mobility model of UCLA students, because the latent states are mostly centered around the UCLA campus. And if you look at the text description of each state, you can find those states are very related to school life. For example, in state 1, it includes keywords like school, UCLA, course, midterm, classes, and those kind of stuff. We have also plotted the transition matrix from state to state, and we find that the transition makes a lot of sense. For example, the transition from state 0 to state 1, which corresponds to moving from apartment to school, have a very high probability. And for the second group level mobility model, it corresponds to the model for tourists in Los Angeles, because the locations of the latent states are centered around airports or some tourist attractions, such as Universal Studio or the Venice Beach, those kind of different points of interest. If we compare those 2 different models, we can see there are indeed different user groups that have totally different moving behaviors. And our model, GMove, can successfully find such groups and build informative models for different groups. In the final set of experiments, we perform a quantitative evaluation by the location prediction task. In this task, we assume the location history of the user is already known. Then, based on this context, we predict the next location the user is going to visit. To compare with GMove, we use 4 baseline methods, where law is a baseline method using the physical law of human movement. And Geo is a baseline that trains one hidden Markov model that only uses geographical and temporal information. And single is a baseline also trains one single hidden Markov model but use all the information. And no-aug is a simplified version of GMove that do not perform text augmentation. By comparing the prediction accuracy of the 5 method, we can see GMove achieves the best accuracy. And we can see the 2 strategies, which is group-level mobility modeling and also text augmentation, are both useful to improve the prediction accuracy. So to summarize, we studied the problem of group-level mobility modeling using Geotag social media. We have proposed the GMove method, which have 2 important strategies. The first one is to alternate between user grouping and HMM training to obtain group-level mobility models. And the second strategy is to leverage keyword spatiotemporal correlation to reduce text sparsity. In our experiments, we have found that it can indeed find group-level mobility models and performs well for location prediction. So this concludes my talk. Thanks.
Thanks for the talk. And near the beginning, you said that you discretize your space in terms of the location and the other features that you're looking at. I was wondering if you have guidelines on how to do that, how to choose the level of discretization, let's say, and how, if you have studied how that affects, let's say, the performance of the model.
So the question is, how will the parameters of discretization affect the performance of our model? Actually, we have tried different parameters of the discretization granularity. We find that we can not do it at a very fine granularity. nor a very coarse granularity. We need to use a granularity like for the spatial and temporal dimensions, we use about 50 bins. Then it achieves the best performance. But it's not very sensitive. I mean, if the range is among like 10 bins to 100 bins, the performance is almost the same.
Thank you.
If you could just clarify a little bit about the text part. Once you get the text information, does that help with the grouping, or is it independent? Like once you get the mobility, then you use the text information to find out what they do. Just want you to clarify.
Okay. So for the text part, if you look at this flowchart, we have two modules that handles the text part. First one is the text augmenter, which takes the original raw geo social media records and augments the short messages. And after augmentation is done, then we go to the HMM training part, where we try to model the emission from the latent state to the specific keywords. We use the multinomial distribution to model the text part. Okay.
I have. Can you explain more on how many groups you determine and how many members in one group? Is there some optimization around how you're grouping?
Okay. So for the parameter of group numbers, we do not do the parameter search at a very fine granularity. We just try to vary the number from 10 to 50. And for the number of groups, it's automatically determined by the Hidden Markov Model ensemble learner, because during the HMM learning process, we do not use hard partition. Instead, we use soft partition. For each user, we compute a vector that represents the posterior probability that the user belongs to each group. So it's a soft partition.
Do you think for future research it might be useful to try and get multiple word phrases together, at least check proper nouns by uppercase in the first word? You know?
Yeah, definitely. Currently, we just do simple stemming and stop words removal. But it's definitely interesting to consider phrase as a basic unit. Yeah.
Any other question? Actually, maybe I can ask the last one.
Okay.
When you do this user grouping and HMM training together, I'm wondering, do you have the assumption that the user groups are kind of similar size? I mean, is it possible that some user group is big, having many users that have similar travel patterns, and some user group is very small, which consists of few users?
Yeah, that's a very good question. Indeed, we find that in the results groups, some groups have much larger size, but some groups have a smaller size. But currently, we do not have some constraints on the group size, so we do not handle this situation.
Thank you.
Thanks.
Okay, so if no further questions, let's thank the speaker again.